In this unit, we consider charges, electric fields, and the electric potential in and around conductors. Electric charge can move freely through conductors, such as metal objects. The human body and the earth are also conductors. When charges move through metals, it is the negatively charged electrons that are mobile. Wood, plastic, stone, and glass are all insulators. Charges cannot move easily in these materials. Another word for insulators is dielectrics. While no material is either a perfect insulator or a perfect conductor, most materials can be classified as one or the other. In insulators, charge can be placed arbitrarily. According to the definition of an insulator, the charges can't move. On the other hand, in a conductor, charges are free to move. As a result, any excess charge must reside on the surface of the conductor. To understand why this is true, let us consider the electric field inside a conductor. Here is a metal rod containing many electric charges. This figure shows all the charges, not just the excess charges. If the conductor is electrically neutral, it will contain equal positive and negative charges in equal measure. To simplify things, let's hide the positive charges which can't move. Keep in mind that a deficit of negative charge in part of the conductor will result in that parts being positively charged. Next, impose an electric field in the conductor by fixing positive charges near one end. These fixed charges will result in the formation of an electric field that is directed away from them. The electric field will cause the negative charges to move toward the fixed positive charges. The negative charges will accumulate near the fixed positive charges, and the electric field will decrease. The charges will continue to move until no electric field remains. The mobile charges in a conductor move almost immediately to cancel any electric field there. In a steady state, which by definition has no moving charges, there can be no electric field inside a conductor. We are looking closely at part of the surface of a conductor that has reached a steady state. Suppose the electric field had a component along the surface. In the presence of this component, a component of the force on the charge directed along the surface would also be present, and this would accelerate the charge. F perpendicular is the component of the force perpendicular to the surface, and F parallel is the component parallel to it. Because these forces cannot be present in a steady state, the electric field must be exactly perpendicular to the surface everywhere. Recall that the electric field is related to a gradient in the electric potential. If there is no electric field inside a conductor, the electric potential V must be uniform. The surface of a conductor is an equipotential. As an analogy to the electric field and potential inside a conductor, consider the surface of a fluid. If the surface were not flat, gravity would eventually flatten the surface. An undisturbed fluid surface is flat. It is an equipotential surface with respect to gravity. Suppose we have two conductors, one charged and one uncharged. The surface of each is an equipotential. If we connect the two conductors with a conducting wire, the surfaces of the two conductors and the wire must be an equipotential. Charges must flow from the charged to the uncharged sphere. Gauss's law can be used to prove that any excess charge on a conductor must be on its surface. Here's how we do this. Define a surface just inside the surface of a conductor. Gauss's law relates the charge inside that surface to the electric field on the surface. Because the electric field inside a conductor is zero, the charge enclosed by any surface inside the conductor is zero. Therefore, any charge on the conductor must reside on its surface. If a cavity were carved out of the inside of a conductor, there would be no electric field in the surrounding conductor and no charge in the cavity. Therefore, there would be no electric field in the cavity. A person inside a metal box would not be shocked, even if the box were charged to a high voltage. Let a hollow conductor have no net charge, but place a charge Q in the hollow region. Construct a Gaussian surface outside of the cavity but inside the conductor. Gauss's law relates the electric field on this surface to the charge enclosed by the surface. The electric field is zero at this Gaussian surface, which is inside the conductor. Therefore, the net charge enclosed by the conductor must also be zero. There must be a charge on the inner surface of the conductor, Q sub s, which is opposite that of the charge Q inside the cavity. The net charge on the conductor is zero. Therefore, an equal and opposite charge must exist on the outer surface of the conductor. The charge on the inner surface of the cavity confines the electric field to the cavity. The location of the cavity, therefore, does not affect the distribution of charge on the surface. The charges on the outer surface arrange themselves in such a way that the electric field inside the conductor is zero. The external electric field is the same as if the charge on the outer surface of the conductor were the only charge. A metal sphere is located inside a cavity of a second, larger sphere. The inner sphere has 0.10 coulombs of charge, and the outer sphere has a net charge of 0.08 coulombs. What is the charge on the outer surface of the larger sphere? Correct. Here's the solution. Next, we demonstrate the simple relation between the charge density and the electric field at the surface of a conductor. Define a closed cylindrical Gaussian surface enclosing a small volume near the surface of the conductor. The flat caps of the cylinder have area A. The charge per unit area on the surface is sigma. In general, sigma varies from point to point over the surface. The charge Q enclosed by the cylinder is sigma A. However, we know from Gauss's law that the charge enclosed by the cylinder is equal to the flux of the electric field through the surface of the cylinder. The electric field inside the conductor is zero, and because the electric field must be perpendicular to the surface, no flux pierces the sides of the cylinder. Only the outer cap of the cylinder contributes to the integral. The electric field is perpendicular to this cap. Therefore, the flux through the Gaussian surface is equal to the magnitude of the electric field, E, times the area of the cap, A. Substitute the charge in terms of sigma into this equation. Solve for the magnitude of the electric field near the surface. It is proportional to the surface charge density. Air breaks down electrically, and a conductor will emit sparks when the electric field reaches about 3 times 10 to the 6th volts per meter. What local surface charge density would be required for the electric field to reach this level on a conductor? Correct. Here's the solution. Consider a charged spherical conductor. The charge must lie on the surface of the conductor. Because of spherical symmetry, the magnitude of the electric field is a function only of the distance to the center of the sphere. The electric field outside a charged conducting sphere is the same as that for a point charge located at the center of the sphere. The electric field is zero inside the sphere. In the equation shown, E is the magnitude of the electric field at a distance r from the center of the sphere, Q is the charge on the sphere, and capital R is the radius of the sphere. Here is a graph of the electric field magnitude as a function of r. At the surface of the sphere, the magnitude of the electric field jumps from 0 to its maximum value, and then decreases further away from the sphere. Here is a plot of the potential as a function of r. The electric potential outside the sphere is the same as the potential of a point charge. The potential inside the sphere is constant. When two conducting spheres are connected by a conducting wire, their surfaces will have the same electric potential. By setting the potential at the surface of each charged sphere equal to one another, we can relate the charge on the surface of each connected sphere to the radius of that sphere. A metal sphere with a radius of 5 centimeters is connected by a conducting wire to a second sphere with a radius of 2.5 centimeters. The sum of the charges on the two spheres is 4.5 coulombs. What is the charge on the small sphere? Correct. Next, we derive a relation between the electric field on the surface of each of the two connected conducting spheres. First, we take the ratio of the two surface electric fields. We know that the electric potential on the surface of the two spheres must be the same. This equation can be rearranged to yield an expression for the ratio of the charges. Substitute this ratio into the expression for the ratio of the surface electric fields of the spheres. This equation indicates that the electric field is higher on the surface of the smaller sphere. On a charged conductor with the shape shown, will the electric field be higher near A or near B? Correct. The electric field will be larger on pointy parts of a conductor with a small radius of curvature than on smooth parts of a surface. Therefore, electric discharges will tend to occur at pointy parts of a surface. Consider an uncharged conductor. If we immerse an uncharged conductor, such as this sphere, in an electric field, what will happen? The electric field must remain zero inside of the conductor. Surface charges on the conductor will exclude the electric field from the interior of the conductor. The net surface charge on the conductor must remain zero. Surface charges will arrange themselves on a conductor in such a way as to cancel external fields. If we bring a charged particle near a conductor, the electric field from the particle will be excluded by surface charges from the region inside the conductor. This is reasonable because charges of the opposite sign will be attracted by the charged particle. What is the electrostatic force on the charged particle? The particle is attracted by the negative charge on the sphere and repelled by the positive charge on the sphere. The positive charge is equal in magnitude to the negative charge, but it is further away. As a result, there is a net attractive force on the particle from the conducting sphere. If the conductor is grounded, charge with the sign opposite that of the particle will flow from the ground into the conductor. The conductor thereby acquires a net charge. This process of charging is called charging by induction. If we disconnect the charged sphere from the ground at this point, it will retain its net charge. The positively charged particle is attracted to the negatively charged sphere. The Electrophorus is an interesting example of charging by induction. A removable metal plate rests on a flat insulator. The insulating base is rubbed with silk, which gives it a positive charge. The metal contacts the plastic at a few points and acquires very little positive charge. When the plate is grounded by touching it, however, negative charge flows onto the plate. As we already said, this process is charging by induction. When the contact is broken, the plate retains its negative charge. When the plate is removed from the base, it can be discharged into a grounded conductor. Because the charge on the base is not removed, this process can be repeated many times. Because an attractive electrostatic force exists between the metal plate and the base, work is performed when the plate is removed from the base. This is the energy source for the static discharge.